Oh, hello, 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 Amanda. Hello, Ardell. Hello, Brian. Hello, Farina. Hello, Rick. Hi, Cynthia. Hi, Rachel. Hi, Viola. Hi, Leslie. Hi, Aaliyah. Hello, Brian. Isn't this weird that I'm doing this? But it's like better, right? Hello. Who did I not say? I see? Isabella. I see? Hello, Brian. Whose name am I still mispronouncing? Hello, Leslie. Viola. No, actually, is that ever? Oh, two more people. Sorry. Hello. Oh, and okay. Sorry. Hello. Who else? Who we just? Hello, Ingrid. Hello. Hello, Langley. Can you? I'm sorry. I'm not Mr. Lou or Ms. Langley. I can't. Can you tell me how to say it again?
Billy. Hey,
Oh,
hey, Fuzzer.
oh, see. Oh my God. Right. I'm totally embarrassed, but I'm glad. See, this is why I'm glad I'm
So
okay.
good, so good.
Right. You're you. Yes, you are you, and I am he, uh, and I'm and we are they, and I am the walrus. Did I ever tell you people, by the way, so my name is Yaverbaum. I'm sure I've told you that, but we're stalling here while more people come in, or warming up while people come in. My name is Yaverbaum. It rhymes with cadaverbaum. First of all, one thing about that, it's an unusual name, right? Like it's not a common name. You may not even know anybody else named Yaverbaum besides me. I don't. Anybody I know or have ever heard of, like even in a web search, but with maybe one exception, anybody I know who has Yaverbaum is related to me in a way that I know. Like I've never heard of a Yaverbaum that is not in my family somehow, which almost suggests, it will almost make that like somewhere that I might have two grandparents or something that were actually cousins and married each other. And in fact, that's totally true, but and explains a lot about me, doesn't it? Okay. But that used to be okay back in the day, like in Brooklyn. Uh, okay. So we're all here, or those of us here. And oh, one last reminder too, if you're in this class, but please make sure that you're in the Google Classroom part of this class. If there's anybody here who's hearing me right now, who has found the Zoom link, and I guess the Zoom link is hard for people, but if you found the Zoom link and you're here, but you need to you ask me for the Google Classroom code, or you need to private chat me or something, make sure you're on the Google Classroom roster. Otherwise, like you'll never get grades and all that. Okay. That said, what we're going to keep talking about springs and everything today. Wait, you can hear me, right? Did we? Oh, yeah, Billy. Yeah, he talked, right? So you can hear me. Okay. We are going to keep talking about springs. It's going to start getting a little more mathy. It's going to start moving a little bit more next week. But still, before we get into the thick of things, just to catch up with ourselves, um, uh, I think now I'm pretty happy to say that I'm pretty sure just about every single one of you totally turned in a whole sheet for homework one. I mean, a whole document for homework one for a thing on a spring. Again, we're still talking about it. We have by no means finished going over it. By no means have we finished going over it. But you all did your job and made your attempt at it and turned it in. That's good. I believe you've all now gotten it back. This was actually me, not Professor Lou. I mentioned it might be her, and it might be her from time to time, but I ended up doing this one. Um, Let me make this clear because I think you did all get them back and they were all very good. It is what I'm looking for. But because this is physics 2 and we have to get going, it's true that in many of your cases, I might not have given you a 50. You might not have gotten a 50 in every single case. If you didn't get a 50, I tried to make it as clear as possible that you can totally just fix whatever I'm asking you to fix and resubmit, and then you'll get a 50. Like it'll just be changed. No harm, no foul. But I want to make sure we're all doing this like the right way. By which I mean, and now that I've looked, okay, so I hate to be obsessive about this, but please do your work on separate blank sheets. Now, forget all my PDF mania. I like overstressed about that. I don't care if it's a PDF or not. You could do it in a Word doc, you could do it on a regular piece of paper and then photograph it. Whatever. But what I'm trying to say, and now that I've seen enough, I know this kind of is perhaps an issue or confusing. Please don't take my question sheet and then try to write on that. Not because you're defacing it, not because you're not allowed to. use it or something, but because it just doesn't give you enough space to think. If you do some clever thing of like recopying it and spreading it out, then fine. I don't care if you're copying my questions and inserting them, but please give yourself more, like, don't confine yourself to any finite amount of space. You should be able to kill a lot of trees when you're doing physics and just write down things until you figure things out. It's hard enough to work with a time limit. Don't work with a space limit. So anybody who didn't do that, I'm not trying to criticize you. Maybe I wasn't clear at first. If you wrote out your answers, no matter how clear they were, whatever, if you wrote them out on the sheet, I'm asking you to resubmit it to get the 50. One of you can tell me, I haven't tested this. I forget what it means to resubmit. If I may have to open up a new portal for you, which I'm happy to do. Wait, do I have to do that? Someone might even want to test. If you're getting bored while I'm talking right now, for real, one of you, if you want to test, if you've gotten a homework back, especially if you just got like a 42 or a 47 or something, you might even want to test right now. I forget how this works with Google Classroom. Like, I'm telling you that if you just resubmit a new document, I'll change the grade. But
yeah, Professor?
Yes, I'm listening. Yes.
I think you can just add or create and then press resubmit, like add another document, but then title it like resubmission or something.
Yeah. Okay, thank you. That does sound right. And I want to go with that. I hope you're right. I think you're right. Retitling it is a good idea to everybody. And then if I'll say this right now too, while you guys right now, I don't think you guys are behind at all. It's good. Like, and in fact, some of you are a little bit ahead of me now, but also I don't think I'm behind yet, like having graded these all. So I'm going to say this. What I'm concerned about is if any of you do redo, if you don't get it back from me like tonight or something, if any of you, especially if very shortly, like even during class, if any of you didn't get a 50, and then you just redo what I'm asking. Or by the way, in some cases, one of you or two of you were clearly just missing a page, then I'm sort of confident you did the page because you'd be like missing the first page and you gave me the second page or something. So probably it was just an accident. So probably it would just take you 2 minutes to fix. If that's the case, definitely one of you test this. I mean, I think Isabella's right, but I'm also, the only thing I'm concerned is I might not get notification. So I'm wondering if I'll even notice that you did this or not. So if you don't hear back, get a redo of your grade within the next couple of days, then please, whoever you are, anybody, either send me a text, maybe that's best. Maybe do send me a text because I'm not exactly sure how this works. And ideally I would, anyway, you get what I'm saying, but I'm telling you all, I don't care how long it takes you to get a 50, you can get a 50, but I do want you to get into certain like physics habits. So do the work on a separate sheet of paper, separate sheets, whatever kind of sheets they are. That's number one. Number two, please, all of you, and again, most of you are doing this, but most of you are circling your final answers to stuff. Like you're showing work and then you're putting a final answer. Even if your work is only a couple of lines, I get it, but then you're circling the final answer. Please do that. That's actually maybe seems kindergartenish, but it's super important for a lot of reasons. Especially it's important as this homework begins to get maybe a little bit harder or something, as you might be growing less confident of your final answers, like that's where people tend to start not circling their answers when they're less secure about them and they're less proud of them. So they don't want to call attention to them, which makes total sense. And especially if I'm telling you all, which I am, that I don't care if your final answer is right or wrong, I could still give you a 50. It might be very easy to infer from that I don't care what the final answer is. And so then you might not circle your answer. I want to send you a very subtle mixed message here. Like, I mean, if there's a fine line here in science. It is about the answer in science. Make no mistake. Like we don't just think this is all like, a matter of opinion and interpretation. It's all about the journey. It doesn't matter where you end up. Like, no, like it does matter where you end up. What I'm saying is it doesn't matter if you end up in the right place or the wrong place, because we're here to learn and because we're experimentalists and researchists. So we should all be comfortable with landing in places we didn't intend. But we got to land in a place, right? You got to circle in. This is not a criticism yet, but it's already, I'm starting to see how people will start fading out on the answers. You really want to circle your answer, almost especially when you're not sure if it's right. Because here's the thing. So we're going to, go back to going over this sheet in a second, but say like question 4 on homework 1, question 4, I ask, what's the speed instantaneously of the object at equilibrium? And the correct answer to that, the instantaneous speed, is like v approximately, because 3.87 meters per second, right? That's the correct answer to question 4. I can't remember, I think we went over it, but V equals 3.87 meters per second. So now say for some reason you get V equals 5 meters per second. Say even you have some sense you probably didn't do it right or you made a mistake, you definitely want to boldly circle that 5. And the reason is because what's really right that you might not realize is what you're rightfully telling me is that you've gotten a speed measured in units of meters per second. What you're boxing really, and with pride that is justified, is you're telling me you totally get what the question is and what type of answer it's looking for. You're just also maybe saying inside you're a little worried about numerical accuracy of your answer. But to be able to make it absolutely clear that you know what the question is a huge thing in science. It's super important, that type of communications. Like in a research article, you constantly are making clear what the conclusion is. Sort of only everybody else only cares about the details once they want to start arguing with you and challenging you. So you're always driving home like what the point is. And the point is the answer. Again, I want you to be comfortable with wrong answers. I want to give you full credit for a wrong answer, but I want your answer to tell me that you know what the question is, like what type, get it? So please circle your answers. So that may be also a place where I took off. Also, please, last thing where some people, and I may not have given you a 50 if you didn't like address the last question, for example, at all. The last question's hard. I have not started talking about it yet. We're going to spend a lot of time on the last question. It is hard. It's so hard that in a way, again, I almost think that if you get the whole last question totally right, like you couldn't get it right just based on anything I've said so far. That is all recognized. But at the same time, you want to make an attempt at the last question. You want to show me that you know what I'm asking for, the type of thing that would qualify as a correct answer. One thing you can do if you're super in doubt. So a lot of people left question 9 blank, or some people did. Therefore, maybe they didn't get 50 points. Again, just make an attempt, resubmit it, you'll get 50 points. Oh, sorry, lots of people. Sorry, I'm losing my mind. I mean, I'm losing my thread here. But as long as we're talking about like we're only on homework 1 here, we still have to talk a lot about it. But no, homework 1 starts kind of straightforward, but all the way already on homework 1, by the time we get to the last question, we're into territory that requires a lot of thought. It really does, like the last question. So it's there to start getting us used to what it means to do stuff when we don't know how to do stuff. Like I didn't teach you how to do question 9, but the first physicist who ever did question 9, no one taught him either. He had to figure it out, or she had to figure it out. It was a he in this case. And the thing is, when they figured it out on their own, by the time they got a right answer, weirdly, even though they didn't have anybody to show it to and check it, they knew their answer was right, because that's like the weird thing of how science works. You figure out things without figuring out how you're going to figure it out. You figure it out. And then even though you didn't know the answer before, once you get it, you actually know it's right when you're doing things right in science. That's what we're like trying to learn here, that mystical art. Question 9 begins us in that process. I don't need to see a right answer from you. And I definitely don't need to see any of you like cheat your way to a right answer, but I need to see a process unfold in, say, question 9. What does that mean? Like, how could you even start question 9? I mean, I'm skipped. I know we haven't gotten to it yet. We'll be there in a minute, but how do you start any question if you don't know how to start it? First thing is make it clear you know what the question is, right? Which, like if you're looking for X, if you're looking for in question 9, we're looking for the position when time equals 1. So you could literally write down something like t equals 1, x equals question mark. Okay, that's the question. That shows me you know what you're looking for. Now, you may not know what to do. What first step should you do if you don't know what to do? Well, the first good step always is to define a term. When in doubt, define a term, perhaps a term in the question that is both important and possibly confusing you or intimidating you. If it's intimidating and it's important, maybe what's intimidating is you don't quite get it. Start by defining a term. If you write down a correct definition, remember, a correct definition is always right. At worst, maybe it's not as relevant as you think, but it's still right. So it's point worthy. Just writing a definition gets you points and gets you one step closer to the truth. Again, we're going to apply this to question 9 in particular, but there's a kind of always something to say, even when you don't think you know the final answer. And if you have in mind what kind of final answer you're looking for, you can kind of always inch your way forward from definitions and inch your way backwards from the kind of answer you're looking for. And even if your middle is a little bit blank, that's a real structure of work right there to show, even when you think you don't know what you're doing. But last resort, say you really do think you get what a question's asking for, but you really don't. You really think you have no idea what to do. Like often that's because you Like if you know what it means, and you know a question's asking for a speed, but you in this case don't know how to get the speed. Well, obviously in a lot of cases you do know how to get the speed, but in this case you think you don't know how to get the speed. This is an example I'm saying. Say you know the question's looking for a speed, but here you feel like you don't know how to get the speed. If nothing else, one thing you could write down is the speed, you could write down an example of an answer that you know to be wrong. You could say something like, V final does not equal 0 meters per second. I know that much. I know that would be a wrong, that's an example of what would be a wrong answer. Even by writing that, again, you're showing that you know what the question is. And if you start to explain why you know that answer would be wrong by eliminating one wrong answer, you're probably getting yourself closer to what the right answer is, but you're giving really valuable information. Like that's also just something to do when you don't know what to do. Last thing you might have noticed, I put in the Google Stream a sheet called Knowing What to Do When You Don't Know What to Do. It's kind of a wacky sheet I made for a conference a long time ago. It's like hard to read in a way and kind of overly cutesy, but it's trying, if you read, it's just for reference for later when you have a moment. But when you're stuck, look, the sheet is giving tips and suggestions for things to do when you're stuck, even if they're saying it in an overly cutesy way. And that's all about what we're really trying to learn here, right? As research scientists, what to do when no one's told you what to do. If you're really, okay, that said, I think, oh, last thing, sorry. The game assignments, I tried to clean up the numbering. I did like retrofit the numbering and the due dates in a way that might have jostled people. Like, oh, so again, you're all caught up. Homework 1, you all turned it in, great. For 50 points, you could turn it again. Homework 2, some people have turned in, great, and I gave them credit and recognition for that. But you'll notice I reorganized. So homework 2, that math methods sheet, I'm not technically, it just got rescheduled or whatever for our next class, which is not even next Monday because we don't have school Monday, it's next Wednesday. So you have one, it's a kind of a thick sheet, and you will have to figure out some things on your own. In that math methods sheet, there's a section about dot and cross products where it just gives you a definition and asks you to work with that, kind of like other sheets in physics 1 do. And that's what I'm asking you to do. Do your best to just use the definition on the sheet and try to get answers based on that. That's due next Wednesday. Nobody is late with that at all. That's due next Wednesday. Anybody who did hand it in has handed it in early. That's terrific. But with the game assignments, I renumbered them in a way that's meant to be clarifying. Here's what I'm saying, but it might have jostled people because they might now think they're late with that. There's no lateness with that. What I'm saying from here on officially is this: we were all in class together on class number 1 last Monday, like 3 class last Monday, we were together in class. On that day, I gave you the first game turn, and you in class like all filled it out, and you all got it back that day. So turn 1 applied to your class participation for day 1 of class. Then we had class 2. So in retrospect, so I'm just, to make things easier, I'm saying, okay, here's the idea. From now on, you all turned in the one for class 1 by the end of class 1. So technically, whatever class participation you did for class 2, I'm saying technically that was due 20 minutes after class on that day. Again, I don't care, but that I'm saying, just so your record keeping, your little note for your class participation for the second class was due a half hour after the second class. Then we had class 3 2 days ago. So technically your participation for that day was due 20 minutes after that class. Now it's class 4. So technically I'm saying, hand in your, or 20, whatever, 5 o'clock, whatever I said. That's just technical. Again, just to keep it organized. So every day, the next class, class 5, there will be turn 5 for you to do the same. You can never hand any of them in, it's fine. Or if you want to, you can retro now hand in last week's, it's fine. I'm just keeping them ordered like that so you can see it, but I don't care when you hand them in. And any of the ones that don't have a number and have some funky title, again, I hope this is clear, are extra other ways to participate that will just sit there. Those are all due at the end of the semester, just to make that clear. You can turn them in at any time. But like, for example, you saw one go on your stream today that had some cutesy title like Speak Now or Forever Hold Your Peace or something. And I'm just saying there, so for example, if someone like Isabella today said something, right? So first of all, that means she participated. So absolutely at the end of today, on that 50-point sheet that says turn 4, she can scroll out her little note. I said something today, that counts as 50 points. But also she can notice, oh yeah, but I used my voice. So that also counts as the special thing of using my voice. Like even though it was one and the same contribution on that separate portal that says you get 75 points if you use your voice, she can fill that one out with the same entry and double dip and turn that in, and she got 75 points for that. And I'll put out more of those if you need more of those. But so again, anyone that's not numbered is something for a special thing that you can fill out anytime if it applies to you. If any of you can at any moment ever think of a way that you want to participate or share that I have not thought of, just put in the private chat and tell me, and I'll make a portal for that, et cetera. But anyway, the numbering system just means from now on, technically each next one is due. The idea is that you would just jot it down right after class. Again, I don't care how you do it, but that's just how I'm numbering it. Are there any? Okay, I think that's all and we said when the midterm is. Sorry, I totally want to get to the spring, but I think that's all the administrative materials. Are there any other administrative questions or Zoom questions or grading questions or anything or registration issues I should know about? Anything? Pause for one second. And if not, we'll just look and say, okay, nothing, we're good, we're good. So I'm going to go on. All right, so we're going to go back to a thing on the spring. Can you remind me? I think in this class, I think we were up to question 5. We had just done question 5 and now we're up to question 6. Is that correct? Not correct? Fair? Not fair? Bueller. Could someone tell me where we're up to and going over a thing on the spring? Wait, have you not been able to hear me this whole time? Yes. Wait, am I on mute? Is anybody hearing me? Bueller.
Yeah, we're hearing you.
Oh, okay, thank you. Okay, so where are we? I believe we're on question 6, but I have 2 sections. Can you clarify or confirm or deny? Are we up? Like, where are we up to? Where should I start? Like going, or where would people like me to start back on going over the sheet of thing on the spring? Wait, what's wrong with my question? Something's wrong with this question. Oh, am I right that did we start going over sheet 1, a thing on a spring? Did we start going over that? Yes or no?
Yeah,
I don't remember exactly. I could be wrong. But I remember we got up to like question 2, and then there was just a lot of questions, like random questions people are asking. So you just started explaining a lot of concepts, but not exactly discussing questions.
Okay, wait, no, that's totally fair. If that's true, that's what I want to know. I'm not, if I didn't actually go through, I want to actually go through these questions with you people. So if that's true, so I started on, could anybody else confirm or deny? Like,
Actually, I lied. I think it might be
we got
question
up to
4.
2.
I remember asking about the diagram, like that was a
Oh, yeah.
good portion of the class, but you did say the answers for 1 to 5, but I don't think you really went over them specifically, except maybe 1. I definitely think 1 has been established, but the rest are kind of just brief.
Okay, no, that's totally fair. And okay, good to know. All right, then let's, and I'm assuming people do want me to. So I'm going to try to be straightforward about this. Again, at any time, if you people are like, yeah, it's obvious, please move on. You can send me in a private chat. Okay, any of you, if you think I'm dwelling too long on something, you can private chat me, like speed up, yo. But all right, I'm thinking then from what you guys are saying, sorry, I'm thinking then we're gonna, I'll start straightforwardly going through this. Sorry, starting with, well, I'll start with question 1. Okay, here we go. Okay, I'm not going to re-explain. I do remember how we did talk about the diagram, so I'm just redrawing it quickly for my own sake, really. But yeah, I do remember this now. We talked about this one. Okay, but we have this. And right now, I'm more or less trying to make this look like what you would make it look like when you hand in homework, right? This is a question 1. Okay, oops, sorry. So question 1 is assuming, question 1 is like at the first spot at X equals the initial position of 0.15 meters, what's F, right? That's the first question. And what do I write down for that? What do I write down for that? Oh, sorry. This is the law. This is hook. I think we, and stop me, but I'm going to assume I think we did talk about this. This is the law that governs spring. Okay. Any spring, like the more well-behaved a spring is, the more it actually strictly obeys this. the more springy something is, the more it actually obeys this. By this, I mean this Hooke's law. So this applies here to this spring, right? And so we're asking for when this is the answer to the first one. I mean, kind of a plug into it is, strictly speaking, it is negative. I think maybe we talked about this. If you assume that the 0.15 is positive, if you like, I am definitely making a decision here. I'm taking the diagram and superimposing this coordinate system on it. I'm declaring that to the right is positive. Everything that goes to the right, whether it's displacement, velocity, acceleration, for anything that's in the right is positive. Anything to the left is negative. You could make the opposite decision. But every single one of us has to have a conscious decision and stick with it consistently. Like I think we mentioned this, but so I'm saying in this coordinate system, if I call, and so like even if you call right negative, right? If you want to look at it the other way and make the right negative, that's fine. But then you'd have to call 0.15 negative, right? And you'd have to stay consistent with that throughout the problem. So I'm saying, strictly speaking, the answer is negative 30 newtons. That just means a 30 Newton pull to the left. That's my answer to question 1. Okay, and that's sort of how I would do it. It's that those are the lines of work. Question 2 now says, question 2. Question 2 is asking for acceleration, right? So what do I do here? Notice I'm always going to start with a general truth and then try to apply it to the particular facts. So I'm going to start with this general truth about springs, but I also have this general truth about all forces, like the specific spring force is equal to negative kx, but the sum of all and any forces that act on an object produces the acceleration of that object, right? Net force equals that. So I'm going to go to the next page. Sorry. Okay, so next page, just recopying through. So we have F. So this is a general truth. This is a general truth. I'm applying to this situation and saying, aha, in this situation, then this is the case. Now, again, many of you might have gotten this answer just in one step in your mind, and I get that, but I'm just trying to carefully justify what's going on here. Like the spring force is the only force acting here. So it does equal MA. Like MA always equals the sum of all forces acting, but the only one acting is the spring force. So we have this. Okay. Now it happens in this case. We've already done the numbers, right? We had this. I know we've already done this part, but and here. All right. Okay. So I'm dragging this out, but basically we're dividing by 0.3. So we now if that force was net, so you get 100 meters per second squared of magnitude. That's the acceleration instantaneously at that first spot of the spring's motion, at that particular spot that we're calling x equals 0.15 centimeters from equilibrium. At that moment and at that position, the acceleration has this magnitude of 100 meters per second squared, which is like very fast, but not impossibly fast or anything. And it's negative, just meaning to the left, right? We're not saying slow down or anything like that. It is actually a speed up, but the negative means in the direction to the left. Okay, that's the answer to that one. Now we're going to start getting into a realm here where hopefully people do stop me and ask questions. But yeah, I guess I read those answers out. That's how you do them. Okay, now question 3. Sorry, who's here? Okay, question 3 asks the same question again, like what's the acceleration, but now asking at a different spot. So it's just trying to highlight the fact that like, ooh, we better notice right away. There is an acceleration here in this situation. Therefore, there's a change in speed going on. Like this object is going to be getting faster or slower, it seems, because it has acceleration. But let's notice also now the acceleration seems to be changing. Like this is about to become a problem that's not like our typical sort of gravity problem from physics 1 or something. Like whenever we did problems with 9.8 at the beginning of physics 1, free fall, the whole business of that 9.8 number was the idea that no matter where you are in your fall, no matter where you are in a particular free fall motion, you're always gaining or losing speed at the same rate. Here, apparently, the rate at which you're changing speed itself seems to be changing, because like if at this position, for example, I mean, we're going to solve it the same way. We're going to now plug in 0 for a, right? So oh, did I just lose? Oh, okay. So it's 0. Okay. I mean, the acceleration at the equilibrium position is 0. I mean, that's the answer for question 3. And I may have mentioned, wait, do I want to say this right now? No, yeah, well, wait, so that's the answer to 3. Now things are about to get a little bit more, slightly more involved. So before we get to question 4, are we all cool so far? Are we all fine with this so far? Okay. I feel like this is people did. Yeah, thank you. That's helpful. Thank you. Okay, thank you. All right, so that's question 3. Okay, now I keep doing that. Question 4. Now I can say, having very recently seen your homeworks, and please stop me if I already made a speech about this. Question 4, a lot of you got the right answer, and that's good. And a lot of you got the right answer by doing a method that sort of in general has some correctness to it. But a lot of you made some leaps in that method. I wrote something down that ultimately is true, but I'm not sure if you really, it's not clear that you know why it's true or to what extent it's true. You'll see what I mean, but basic. All right. So, but the answer is 3.87 meters per second. That is going to be the answer. Well, let me remind you what the question is. Question 4. So question 4 is now at x equals 0. Okay, we're solving for the speed at equilibrium. So what are we picturing here so far? We're picturing that we let this mass go, like the mass is, we're holding the mass still at this initial displacement from equilibrium. We're holding the mass, initially, we're holding the mass still at a place that it doesn't want to be. Like it's not ground. We're holding it still under the presence of a conservative restoring force, the spring force, such that we know as soon as we let go of this mass, it's going to start moving in toward equilibrium. It's going to be moving faster and faster. It's going to be accelerating toward equilibrium. But now notice this question's asking, what speed do we get? What speed does it attain by the moment it gets to equilibrium? That assumes it'll have any speed at all, right? Which is true. Like it started with no speed, but it's moving faster and faster. By the time it gets to the place we think it wants to be, by the time it gets there, it's not going to stay there, right? We're saying there's going to be some non-zero speed we believe it's going to attain at equilibrium. So just note, things do not necessarily sit still at equilibrium. What they necessarily have at equilibrium is 0 acceleration, as we just found in question 3. So we want to find the speed at equilibrium. Now, one instinct might be, oh, okay, we have acceleration, we're looking for speed. Can we do something like A equals V minus V naught over T, or like one of those one-dimensional kinematics equations from physics 203? That might be an instinct. In fact, it'd be a smart instinct that would show that like you paid attention in physics. One might think, or some other equation like A equals V squared minus V naught squared over 2 X, yeah, or something like that. But none of those, and you might think, we just asked 3 questions about acceleration. It would be very good. It would be very reasonable to suppose that we want to use that acceleration somehow to get a speed, but we don't. And most of you got a right answer here or did something. Most of you did not, suddenly stopped talking about acceleration here and stopped talking about forces and all of a sudden shifted into this other way of thinking called energy. Now, this is a compliment, but I want to point out, most of you, when you got to question 4, or a lot of you, all of us like stopped talking about accelerate. We were just asking these questions about acceleration and force. You dropped that and you just picked up this new solution method, this new topic about energy, and wrote down some things called, like 1 FMV squared kinetic energy or something. Now that's a correct impulse. But I want to stop and ask, do we know why we did that? Like why, especially if the questions are asking about acceleration, which might even lead you to think that you should use the acceleration somehow. Why suddenly on question 4 do we drop the acceleration method and start all of a sudden thinking about energy? Like either why is that necessary or why is it okay or both? And look, and to be frank, for a lot of you, the reason might be because you looked it up on the internet and that's what they did. And that's okay, as long as you then understand what you're doing when you write it down. I should also digress for a minute and be a jerk and say, if you did anything else here, like, so a number of you did write something down here, something that used an omega. At this step, some of you did write down something that had to do with omega or X with a dot over it. Like kx dot, like some of you wrote something like negative kx dot equals like omega squared k or something like that. If you wrote anything down with an omega here in this step or like a dot, then I might there have also not given you a 50, and I might have said something like, please only write something down that you can defend or that you understand. Okay, now again, you can totally resubmit, but this is a gentle way of me warning everybody. If you wrote down at this question something that had an omega or an x dot or something, don't be ashamed of yourself or anything like that. But you got to know that I know that that's all of a sudden out of nowhere. Like we've never had an x dot in this class or something, and we haven't said anything about an omega. So that has to come from somewhere. If you wrote something like that, I mean, presumably it comes from the internet, and that is fine. That's not cheating. That's called research. Like any way that you can answer these questions. But the thing is, if you get something from the internet, like something that has an x dot or you say, you got to then that's helpful to you only if you can then make sense. If it's giving you an idea that you didn't think of before that now helps you, great. But until you look up what x dot means and figure out why that thing is true, or until you look up what omega means, or maybe you also already know, which is why I want to be careful with what I'm saying right here. But like all of a sudden, if there's an omega in your answer, maybe that's because you've studied this before and know a lot or figure something out. But whether it's that or you got it from the internet, you got to kind of show me. You got to make sense out of what you're like. You can't just introduce a new idea or something out of nowhere and without explaining it or without understanding it. In other words, please don't write down something you don't understand. I mean, that's the closest we can come in physics to doing something that I would consider to be cheating, not ethically cheating, like that's between you and your God. And I kind of do mean that for real. But which is why I'm telling you, if you wrote down something, and also, again, I don't mean to accuse anybody of anything. And you're in your heart of hearts, you know why you wrote down something with an omega or an x dot, and you totally can get your points and we can move on. But just as a cautionary thing, especially when we get to our take-home exams, be careful, only write down something that you actually get by the time you're writing it down can justify. So here, what a lot of people did do, I guess to start cutting the chase, a lot of people started making reference to things like this, or something like this. Okay, now this is true. These things are true, and these are a little bit more from Physics 1, although I still feel like I should talk about them. Oh, excuse me, someone's here. But I want to, and they're right, or something using them in a correct way is correct. But before I even, well, actually, I'll write down first of all, the correct way. Here's what I think is the most correct way. I'll just write down and I'll tell you. I think the most correct way to solve this problem is say. Okay, tell me, I'm gonna turn the page. Tell me if you need me to go back to this page. But I'm saying all the forces. Now I'm being careful here, breaking down something, and whether I'm telling you or I'm telling you what you would ideally tell me in your homework. And again, that could be because of resubmission or whatever. But all the forces doing work on this mass are conservative. I mean, there's only one force doing work on this mass, and that force is the spring force, the elastic force, the F equals negative kx force. That is a conservative force. And you're going to remind me a couple minutes how much we've said about this or not, but it is. I may want to backtrack and explain that to you, but it is. The spring force is a conservative force. The only other example of a force like that we know so far in our life is gravity. Gravity is a conservative force. The spring force is a conservative force. Since all the forces doing work on this thing are conservative, therefore, I'm going to turn the page a second. What I'm writing right down right now, I would not expect any of you to have written all of this in the homework you submitted to me. I'm not saying it, but I'm trying to write down something clearly now to everybody to make sure we're as clear and comprehensive about this explanation as a group before I go any further. So I'm saying this so far. I mean, I'm about to turn the page, but I'm saying, okay, first of all, if you're looking at a system where all the forces doing work on that system are conservative forces, or where the only forces doing work are conservative forces, then what we know, what we say almost by definition is the system will conserve mechanical energy, conservation of energy. But what do we mean by that? Like, what strictly does conservation of mechanical, I mean, I'm not asking, I'm telling for the moment, conservation of mechanical energy in physics means, it means that the total amount of mechanical energy is the same from any one place to any other place. I may or may not have said this last week or yesterday, but let me start by, so to be really specific, what I mean by total mechanical energy is the sum of all of the kinetic energy of some system plus all of the potential. Like at any given place and any given time, a system could have a bunch of kinetic energy or it could have a bunch of potential energies of even various different types. There's a different type of potential energy associated with every different conservative force. Only conservative forces store energy in the form of potential. Only conservative forces allow us to say this thing of conservation of energy, but each conservative force has its own potential energy function associated with it. If you add up all the potential energy of a system at any one given place, plus all the kinetic energy of that system at that given place, first of all, we call that total mechanical energy, capital E. So capital E means the sum of KE plus PE. If I ever write capital E sub A, like I'm writing here, like capital E subscript A, what I mean by that notation is the total mechanical energy at some location that we might call X equals A. Like A could stand for a number. It might be X equals 0.15 meters or X equals 0 meters or whatever. But A is a location. B is some other location, X equals B. Okay. What I'm saying from a physics standpoint, if and when a system conserves energy, what that mathematically means, like the mathematical way to write energy is conserved, is to write, I mean, so conservation of mechanical energy is written the following way. Again, you wouldn't have written all this the first time you did the homework, but I do need you to see all this to make sure you get the next question right. Conservation of mechanical energy. Notice I'm trying to be very explicit and specific at a subtlety that is often missed, which is I think most of you know, or most of us know, that if we say energy is conserved, what we're trying to say is the total number that corresponds to energy is a constant. Like if we say energy is conserved, we mean there's this certain number of joules of energy and it like never changes, right? And somehow and that's what we're always looking for in physics, is some feature of a problem that's not changing while all the other things do. We're always looking for something that's constant. If we say energy is conserved, we mean it's a constant. But what I'm trying to add to that right now, I'm trying to specifically say, if you say that energy is a constant in physics, you mean we mean from place to place, like as opposed to from time to time. To be really as clear as I can, I'm making a contrast here. Sometimes in physics, we say momentum is conserved. We say linear momentum is conserved. That's a big law. That's a principle. That's important. Momentum kind of looks like energy is like 1/2 mv squared. Momentum is like mv. Like they can be very similar. But when we say that momentum is conserved, we mean the total amount of momentum at any given one instant in time is the same as the total amount of momentum at any other given instant in time. That's how like momentum works. What I'm saying here in contrast is whenever you want to think energy, specifically think the total amount of energy over here at one place is the same as the total amount of energy over there at some other place, like specifically. And that means, well, yeah, that's what it means. So in this case, say for a spring, that means sorry, wait, sorry. So K, E, and P, like what's the deal? Well, yes. In physics, until in anything we do in physics in these two in classical physics, kinetic energy of an object is always 1/2 mv squared. Always. You can memorize that and it won't fail you. Any system, any object, that kinetic energy is the ability to do work by virtue of motion. So the more motion you have, the more kinetic energy you have, the more V, and the more of you that there is, the more kinetic energy you have. So kinetic energy is always 1/2 mv squared of any system at any given place. But now potential energy can differ from conservative force to conservative force. The kind of potential energy we mean here is the potential energy due to a spring, as opposed to the potential energy due to gravity. The potential energy due to gravity is often written mgh. Some people put that in their solution. That's applicable in situations, but not this one. Gravity is not playing any role here. The spring is playing a role. The potential energy due to a spring, and I don't remember if I'm right this moment, I'm going to say it, but we have to get back to why this is true. But spring potential energy is always 1/2 kx squared. Again, if you're following me so far, but you're a little shaky on like where I just got that, like why is that, then fair enough. And I do owe you a bigger explanation, but it is true for the moment that spring potential energy is always 1/2 kx squared. So strictly speaking, to do this question 4, again, I'm over talking this for a reason, but I'm saying the statement of truth that we'd want to start off with in question 4, in problem 4, would be this. We're going to say, so back to question 4. Oh, okay. So question 4, we're going to compare two places, A and B. They can be whatever we want. Like what in general are they? Well, the whole point of conservation of energy is it says no matter where you are in the system, you'll have the same total amount of energy. So what A and B always represent is one is a location that you know the information about, and the other location is the one that you're trying to solve for. In other words, to be more specific, location A is one of the locations is a location for which you know the speed, and the other location is the one that you're trying to find the speed at, because mechanical energy is always ultimately a speed position trade-off. no matter what expression for potential energy you write down, you're going to see in a minute, like it's always like the more you move in one direction, the less speed you have, or the more speed you have. You're always trading off where you are for how fast you're going. So you pick two locations. Let's let A be the place we know something about, x equals 0.15 meters. Like we know what the speed is there. It is given in the problem as 0 meters per second. And we'll let location, again, I know you wouldn't have written all this out. I'm just trying to show you what's really going on behind the scenes. Because again, if you didn't write all this out, it's possible you wrote something that by coincidence worked for question 4, but then would get you in trouble in question 5. So again, bear with me. But this is the way to think about energy for real. Let B stand for x equals 0 meters, right? Where we're solving for V, because this is how I'm setting it up. So I say, okay. Like what the statement of truth that is true. Like if I wrote this down, what I just wrote, if I wrote this on an exam, it is definitely true. Even if I don't know what the numbers are of this problem, even if I don't know what to do with it, it's true because it's energy conservation. So I go a step further and say, okay, what's true? What's definitely true, like about any mass on any spring, is this. Now, this line right here that I'm writing right now, honestly, I think pretty much this should be everybody's first line in solving question 4. Like what it would mean to show work in question 4 is really, you have to start with something like this thing that I just wrote. I mean, everything I wrote before was kind of to explain to you guys, the students, but here, start with something like this, okay? As opposed to what I'm really trying to say is don't start off saying 1/2 mv squared equals 1/2 kx squared. A lot of you did that, and I that's a habit that comes from somewhere, but it's like not true. It's not fair. What's true is that all of the energy at any one spot equals all of the energy at any other spot. What's true, and now if we're careful about what those spots are, if we now start analyzing, if I postpone the numbers for as long as possible, I say, oh, spot A was that initial position of 15 centimeters where the speed was 0, right? So at spot A, I say, oh yeah, the speed is 0. The mass just was beginning to move there. And at spot B is the equilibrium position where x is 0, right? So when x is equal to 0, then x is equal to 0. When x is equal to 0.15, v is equal to 0. So I can cross out this term. In this case, what I'm saying is the long sentence I just wrote here is the truth of all masses on all springs. Now, if I'm looking at this particular situation where I'm comparing the initial position to the equilibrium position, then I have this convenience where I can cross out this term and I can cross out this term. So then what I end up writing down is what a lot of you wrote. So I end up saying this, right? But please notice I'm saying this line that I just wrote is derived from the line above it. I can't start by saying this. This line now looks like it says potential energy equals kinetic energy. And that's what people end up often thinking, that energy conservation, like people often get in this habit of thinking, oh yeah, okay, so I set the kinetic energy equal to the potential energy. No, don't set the kinetic energy equal to the potential energy, because in fact, that's not okay. At any given random moment, probably you have a lot of one and very little of the other. They're probably not equal to each other at almost any random spot you pick. What we're saying here is that all the potential energy at position A is equal to all the kinetic energy at position B. That's what I'm trying to be explicit about here. So that, but then sure, you can do your math. Like you can divide both sides by 1/2. That's terrific. So now I go to the next page. So I do have, whoops, sorry, I fire myself immediately. But then I quickly reapply and give myself a promotion. But I forgot to pay myself. It's like all those cartoons, like those Roy Lichtenstein cartoons where like there's a woman who's like, oops, I forgot to get a job or something. But like being a professor is like, oops, I forgot to get a job that actually pays me. Okay. But so what we have here is this. So now I'm saying because of this particular situation, I'm sorry, I crossed out. that, and I crossed out that. What am I solving for? I'm solving for V. So now I can say, and I'm still, now I'm going to do that thing that a lot of you don't like, but I want to try to habituate you to. I'm postponing the numbers. I'm just stalling on the numbers as long as I possibly can. I'm going to algebraically rearrange this to solve for what I'm looking for. Like I'm looking for V. So I go like, oh, okay, V squared equals KX squared. Like, a lot of you would prefer to plug in the numbers first. Please, the stronger you would prefer not to do this, the stronger I urge you to try this, because there's a reason you don't want to do it, which is the very benefit that it'll give. But anyway, then I say, okay, fine. V equals the square root of K. And again, a lot of you had this written down. I know that. Now I plug in numbers, and I know that the square root is not, well, yeah, now I plug in numbers. Okay. And the units do work, which is nice. I mean, they better. All right, go to the next page. Oh, sorry. And again, and I'll pause. I'll take a breath in a second and tell me if you want me to go back pages or whatever. But no, that's not right. Oh, yeah. I'll check my math. Hold on a second. Oh, no. Yeah. This is that's a lot to say. But so that's energy conservation. Energy conservation again is 1 f mv squared plus 1 f kx squared over here equals 1 f mv squared plus 1 f kx squared over there. Then whatever convenient zeros you can plug in, by all means do, cancel out terms. But then we end up with this. One last thing to say about it. What I wanted to ask you guys before, if this is clear, and stop me if it's not clear, I'll look in the chat. If this is clear, we do want to move on, but could anybody answer, like, why did I suddenly start bringing up energy? Like, why wasn't it good enough to keep talking about forces and accelerations? Why didn't we use an acceleration equation or something in order to get the speed? Like, why was it either necessary or okay suddenly to shift gears and start thinking about energy? I mean, that's a tough question, but there is an answer to it. Or if anybody
for me-
want, oh, sorry, yeah, go. Sorry.
Okay. For me, like what you said earlier, I was thinking about like the equations from last semester, like the half equals, all that stuff, like from free fall. But I realized that this wasn't like a free fall equation. Like there's a spring involved, even if it was vertical, like it's not like a free fall kind of thing. So I didn't think that the acceleration would necessarily help. And plus I looked it up and they were talking, then they started talking about energy. So I was like, okay. And when they were speaking about it, they said that like they brought up harmonic motion and how it's like a wave. So I didn't think that it would be like, wow, I don't know where I was going with this. But like I didn't think that it would help like using the acceleration.
And you're totally right. No, that is right. And yeah, and this is going to get us into waves and the harmonic and all that stuff. And I know that I said today was going to be about simple harmonic oscillation. I still haven't even defined that word to anybody, but you're absolutely, yes, this is going to get us into this whole harmonic thing. And there is a reason, you're absolutely right, that it's totally true that somehow I keep comparing things to gravity because the spring force and the gravitational force are both conservative, yet you're absolutely right, or Ardell is absolutely right, that anything we learned about free fall last semester and anything we learned about acceleration equations would not help us here. It's true, even though they're right and true. And even though we spent the first 3 questions thinking about acceleration, the reason we did that, so I'm now saying this to everybody, the reason we spent the first 3 questions looking at acceleration, but then all of a sudden just jumped off the bridge and stopped using acceleration is that the first 3 equations were, or sorry, sorry, yes, sorry, yes, I can, hold on. Yes, is it this page? Great, thank you. Cool, okay, we spend the first 3 questions looking at acceleration. Then all of a sudden, we don't even use the acceleration. It almost seems like it's trying to trick you or something. What the first 3 questions are trying to show really is that the acceleration changed from spot to spot. Not just like once or something, but that in fact, the acceleration is continuously changing. Like for every different X value, there's a different A value. This is fundamentally different from free fall and from all the stuff that we focused on at the beginning of physics, physics 1, like all those original equations and stuff. The reason they all have an A in them is because there's some A value that you can plug in, like 9.8 or something, meaning that at the beginning of physics, we're looking at situations where even though velocity changes, even though there is a change in velocity, which we call acceleration, yet there's no change in acceleration. Like that's what lab 4 in physics 1, that's what the whole string with the bolts is supposed to be about. I mean, this is a hard concept, but remember, constant acceleration means that there's a change, but there's no change in the change, right? It's just a change, not a change in a change. What we're saying now is, things are about to get things are about to get a little bit more tricky now, because we don't just have acceleration, we don't just have changing velocity, we don't just have like a derivative of position with respect to time. We have or even a second derivative. We seem to have a third derivative here. We have acceleration that's changing for every step that the mass takes, from 0.15 to 0. Acceleration is not, so because the first 2 questions are showing us acceleration is not a constant. Therefore, we cannot use constant acceleration methods that when acceleration, I'll write this down, I'm sorry. First thing I'm saying right here is, sorry. Oh, that's a great question, Amanda's question. That's a great question. I mean, my fast answer, like, assuming I do understand that question, so her question, well, yeah, you can read the chat too, but Amanda's question is, would we still have to consider energy if a value for time had been included in the facts? My basic answer is no, you're right, we wouldn't. Like, that most likely, if we knew something about time, we most likely would not turn our attention to the conservation of energy. That really does put in perspective what I'm trying to say. I mean, that is a great question. So, and put another to elaborate on that, what I'm saying here is, Yeah, energy is something that is conserved from place to place. The whole concept of energy conservation is it says you name the place, we'll name the speed, or you name the speed, we'll name the place. It's a speed place trade-off kind of thing is what energy conservation is. Therefore, whenever the acceleration is changing from place to place so that you can't deploy constant acceleration methods, that's precisely when we use energy methods. When specifically, in other words, when we know something about one place and we don't know speed about some other place, is precisely when we use energy conservation. If we were being told things about time, we would probably not use energy conservation. We would use momentum conservation or something else. I mean, that's exactly right what Amanda's saying. One last way to remind you of why this is. So the reason we, like, in other words, if anybody who looked up on the web, like how to do this, and if they suddenly people are using energy, again, I'm not saying you can't look up on the web, but it would be fair for you seeing that to be like, well, okay, great, I'll copy this down, but I don't know where they got this from. Like Yaverbaum's going to ask me why I did this. I don't know why the frick they did this. The habit of physicists is if you want to know, if you know the speed at one spot and you want to know the speed at another spot, use energy conservation. And the real specific reason for that, sorry. Pardon me for 1 second. Come 1 second. I'm sorry. Yeah. What? Hey, dude. Yeah, my class is over in 5 minutes. Great. Yes. Yeah, exactly. Love you. Okay, let me just, now this all of a sudden is looking a little intimidating here. Let me just, I know we've got 5 minutes plus. Apparently there's a couple of, like legendary Pokemons that need battling. So obviously I have to attend. Hold on a second. I'm writing this. This looks out of nowhere when I'm writing, I know. And it'll take a little more explanation next time, but I want to have you have it in your notes, if nothing else. Now, again, I'm aware of the time and I'm aware that I'm taking a slight left turn here for a second. This may look intimidating, or some of you may know exactly what I'm writing here. A quick version of what I'm writing here. I'm just trying to remind you what the definition of work in physics is. Approximately, simply put, work you may recall as force times displacement. Again, there's a little quick overview of something here. Like this first line is sort of saying work approximately is defined to be force times distance. Approximately. Why do I say approximately? And why do I have those triangles there? But first, remember that, right? For work is force times displacement in some kind of way. Like one, just to remind you, 1 joule, excuse me, of work is equal to 1 Newton of force times 1 meter of displacement, right? At a fundamental level, work is force times displacement. But now let me be a little careful about that. Well, actually, I don't want to be too careful. What I'm saying right here is work is force times displacement. Work is force through space. Work is the effect or the consequence of a force acting for a while throughout an interval of space. Like force itself is something that just acts at a point in space and time. When we think of forces and Newton's second law and free body diagrams and accelerations, the whole idea there behind free body diagrams and everything is you picture this one point in time and space and you ask yourself, what are all the forces acting on that point right now, right here at this moment in this position? You add up all those forces that are instantaneously acting and you get an instantaneous acceleration. That's like the force picture. But if, and in other words, the force picture applies to infinitely small segments of time and space. That's why derivatives get involved. To talk about a force is to actually talk about something that's happening at like an infinitesimal interval of time or at a Euclidean segment of space. That's kind of a hard thing for all of us to grasp, and it's very hard to measure. So when we go to the next step, we say, what if we had a force acting throughout some segment of space, like a steady push, pushing a box throughout some measurable finite segment of space, like 5 newtons of force times 3 meters of space. That's the concept of work, right? Work takes force from an infinitesimal, like point-wise kind of affair and turns it into a finite, measurable segment of space. A little bit of work over a little bit of space is force times that segment of space. Now, the rest of the notation on this sheet is what I'm actually trying to remind you that then strictly speaking, that's what you can get away with that definition as long as the force that's acting is a number that you could just plug in like, oh, for 3 meters, I had a 5 Newton force acting for those 3 meters. So, okay, 5 times 3 is 15 joules of work. But if the force is continuously changing throughout that space, which is exactly what we're saying here with the spring, or exactly when actually energy conservation becomes worth considering, if you have a force that's not steady, and again, I'm aware of the time I'm going to stop in like a second, but if you have a force that's not steady, if it's continuously varying throughout the space, then like, how do you get the work? What does that mean? Well, what it means is you got to chop that space into small enough segments, each of which has a force that's not changing that much, right? Like if you want the total amount of work done over a whole big space with a force doing wild things, assume that the total work over the whole thing is the sum of the partial works over each partial segment, and chop it up into bits for which you have, and add up all, oh God, I think this, oh, the board just disappeared. So, well, I think that's the Lord's way of telling me it's about to be 4:20 anyway, but pardon. What I'm trying to say right now is one thing we're going to have to actually grapple with this in this class is if you want to get the work done throughout a whole space where the force is changing throughout that space, as is the case of the spring, what you really have to do, excuse me. Whoa, hold on. Whoa, hello? We are going to wrap in a second, but I'm trying to quickly remind you that strictly speaking, work is the integral of force with respect to displacement. It's like force times displacement for a little bit of displacement plus force times displacement for the next little bit of displacement plus force times displacement for the next little displacement, all added up so you get one big sum of force times displacement. It is all about space. That's why we use energy conservation when we're trying, when the force moves from space to space. We have like 1 minute left, but I don't want to, having said all that, where's this all going? Question 5. It's possible to get question 4 right for the wrong reasons, but then therefore you would get question 5 wrong. So the rubber meets the road in question 5. We're going to end with this. I'm just going to write it down. Question 5, question 5, you do solve it the same way you do question 4. But if you start off question 5 with 1 f kx squared equals 1 f mv squared, like you'll get the wrong answer. Question 5, we have to say the same thing. 1/2 kx squared plus 1/2 mv squared over here must equal 1/2 kx squared plus 1/2 mv squared over there. Let's let A be that place that we know something about. And let B be the place that we're looking for, the place where V equals 3 meters per second, according to the problem, right? So then just note this. We set it up the same way as before. We look at the situation. Oh, okay, at point A, sure, this term here can be crossed out. But at point B, neither of the terms can be crossed out, right? Like this is why it's really important not to memorize just 1/2 mv squared equals 1/2 kx squared. Always start with the whole thing, cross out what you can, but some things can't be crossed out. So what we end up saying here is this: we can divide both sides, but just about there. We could divide. We're going to stop in a second. I'm going to go as soon as it's over. I'm sorry. And if you have questions, please text me or something because I'm going to hop right off this before the Pokemon battles itself. But I can divide, I can factor out a half, divide both sides by the half. So now I literally am left with, we're just going to finish with this. We're literally left with, okay, mb squared A equals, and you could have chosen A and B points differently also, and it'd still be fine. But notice I have something like this now. Now I'm not, you'd think I could subtract mv squared from both sides or something, but no, it's two different V's, it's A and B, right? And what are we solving for? We're solving for that X. So I end up saying, and we're just about, oops, sorry. We're just, of course, I'll post all this and put the lecture and blah, 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 and have a great holiday, next holiday, but we say, okay, kx squared equals mv squared A. And again, you might have chosen different A's and B's and then it maybe works out. But here too, you might think, can I like cancel out the M's or divide both sides by M? But no, because there is not an M in every term. What am I looking for? I'm looking for X. So I do that. Again, some of you might find this looks like a lot, but you have to rearrange and plug the numbers at some point. So I'm just suggesting considering a different order from the way you usually do things. So then we're saying this. Again, we're going to end. And if you have to go, please go. I'm not even looking at the, I mean, if you have to go to a next class, just go. And these notes will be posted. So we have this. Now I can plug in. And I think someone technically speaking, we're going to get two answers, right? I mean, really, it's the positive and negative root of here. Either one will stop for X. But what we end up getting is and you just can't get rid of those 0.3s. They're there to ruin your life. We do this, and you will find that X approximately equals plus or minus 0.0. And yes, please go if you have to go. And it's not rude, please go. And I'm about to go too, but that's what you get. Okay. Oh, and thank you for putting a goodbye. Yes, and goodbye. Thank you. That's all I got. If you're good, I'm good. But I'll pause for a second so you can copy down. Thank you. You guys are great. I miss you already. Have a wonderful day. Awesome. Thank you. Thank you. Oops, I lost.
Thank you, Professor. See you next week.
Yes,
Have a
see you
great
next week. Okay.
day.
You too.
Thank-
You too.
Thank you, Professor. Take care.
Thank you. Cork bless America. May the net force be with you. Awesome. Thank you. Good homework, guys that are still sitting here. Great. Thank you. Awesome. And I mean it. And I remember you actually weirdly. Awesome. Thank you. And I'm going to hop. We're good. We're good. Yes. Awesome. Awesome. Good. Okay. Good. Good. Thank you, guys. Bye, Elizabeth. Okay. Thank you.